Imagine you're listening to the universe. Not metaphorically, literally. You're sitting at a radio telescope in the Australian outback, headphones on, watching a readout scroll data from billions of light years away. The signal is white noise, cosmic static. And then, for less than a millisecond, something screams. It arrives from deep space with the energy equivalent of 500 million suns. And then, silence. It's gone. No repeat, no pattern, no explanation. What if I told you that somewhere in the universe, something is doing this constantly? That every single day, thousands of these blasts are washing over the Earth, invisible, undetected, and completely unexplained? What if the most powerful radio signals in the known universe are arriving on our doorstep, and we have absolutely no idea who or what is sending them? They are called fast radio bursts, and in the 17 years since their accidental discovery, they have defied every explanation physicists have thrown at them. Dying stars, colliding neutron stars, black holes, dark matter. Even, and this has been seriously proposed in peer-reviewed literature, technosignatures from alien megastructures. Every answer has raised three more questions. Every solved mystery has revealed a deeper one. Today we journey through the evidence that challenges everything we thought we knew about the cosmos. We will travel billions of light years. We will confront physics at its absolute limits. And at the end, we will arrive at a question so profound, it may redefine our place in the universe. Prepare yourselves, we begin. In July 2001, a young astronomer named Duncan Lorimer and his undergraduate student David Narkovich were doing something tedious, combing through years of archived data from the Parkes Radio Telescope in New South Wales, Australia. They weren't looking for anything revolutionary. They were cataloging known radio sources, pulsars mostly, spinning neutron stars that blink like cosmic lighthouses. And then David Narkovich found something that didn't fit. Buried in data from 2001, almost invisible in the noise, was a single burst of radio energy. It lasted approximately 5 milliseconds. That's 5,000ths of a second. In that fleeting moment, the source released more energy than our sun emits in 3 days. Lorimer published the finding in 2007. He called it simply a bright millisecond radio transient. The astronomical community called it the Lorimer Burst, and for years many called it something else entirely, a glitch, an error, a piece of earthly interference misidentified as a cosmic signal. This skepticism wasn't unreasonable. Astronomy has been fooled before. In the 1960s, researchers at Cambridge first detected pulsars and genuinely considered the possibility they were picking up signals from an alien civilization. They nicknamed the source LGM1, Little Green Men 1, before the pulsar explanation emerged. So the scientific community waited, and the universe answered. Between 2007 and 2013, more bursts arrived, each one a millisecond flash of ferocious energy, each one arriving from a slightly different patch of sky, each one, critically, displaying a property called dispersion delay. The lower frequency components of the signal arriving slightly later than the higher frequencies, exactly as would happen to a radio wave traveling billions of light years through the thin plasma of intergalactic space. This was the key detail that silenced the skeptics. You cannot fake dispersion delay with earthly interference. Physics simply won't allow it. These signals had traveled incomprehensible distances. The universe was talking. The question was, what was it saying? But the evidence forces us to confront an uncomfortable possibility. The more we looked, the stranger these bursts became. Because some of them, not all, but some, were doing something no one predicted. They were repeating. The repeating behavior was first spotted by Paul Schultz of the Dominion Radio Astrophysical Observatory in late 2015. Researchers using the Arecibo Observatory in Puerto Rico, then the largest single-dish radio telescope on Earth, detected something extraordinary. A fast radio burst designated FRB 121102 had fired again and again and again. It was a repeater, the first ever confirmed. This changed everything because a repeating source could be studied. Scientists could point their best instruments at it and wait, and what they found was baffling. FRB 121102 was coming from a dwarf galaxy 3 billion light-years away, an almost incomprehensibly distant address. In 2017, astronomers published a paper pinpointing its exact origin, a tiny, violent region of star formation, less than 100 light-years across. That's precise by cosmic standards, but it raised immediate questions. What kind of object could survive firing off bursts this powerful, repeatedly, without destroying itself? Consider the numbers. Each burst from FRB 121102 releases in 1 millisecond what our sun emits in about 80 years. Do that thousands of times, and you need an extraordinarily efficient and durable engine. Astrophysicists call this the energy budget problem. Whatever is creating these bursts is operating at the absolute edge of what physics allows. But this represents just one piece of a much larger puzzle. In 2018, a revolutionary instrument came online in British Columbia, Canada, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike traditional dish telescopes that must be pointed at a specific target, CHIME is a fixed array of 4 100-meter cylinders that surveys half the sky every single day. It was not built primarily to study fast radio bursts, but it found them anyway, by the hundreds. In its first year of operation, CHIME detected more fast radio bursts than all previous telescopes combined. Suddenly, scientists had a catalog, and with that catalog, patterns began to emerge. Scientists discovered that the rate of fast radio bursts across the observable universe is extraordinary. Best estimates, published by the CHIME collaboration in 2021, suggest that there are about 800 detectable bursts occur every single day. Every day, the number detectable is a fraction of the total, because our instruments are not sensitive enough to catch them all, and many arrive from directions we're not watching. The universe, it turned out, was screaming constantly. We had simply not been listening. Then scientists discovered something that conventional explanations absolutely cannot account for. In April 2020, astronomers detected a fast radio burst from within our own galaxy. That alone was remarkable, but the source was identified almost immediately. SGR 1935 + 2 154, a magnetar, a neutron star with a magnetic field 1 trillion times stronger than Earth's. This was the smoking gun many researchers had been waiting for. Magnetars, they argued, could produce these bursts through violent magnetic field rearrangements called starquakes. Case closed. Except it wasn't. Because the galactic magnetar burst was, while powerful by earthly standards, roughly 1,000 times less energetic than the most distant fast radio bursts. If magnetars are responsible for the extragalactic bursts, their behavior at cosmological distances would require them to operate at energy levels that push the very limits of known physics. The evidence from CHIME, meanwhile, kept producing anomalies. One repeating source, FRB 20201124A, was found to produce bursts in irregular clusters, firing dozens of times in a few hours, then going quiet for weeks. When researchers analyzed the polarization of its radio waves, they found the signal was twisted and rotating in a way that indicated the source was embedded in an extraordinarily complex, rapidly changing magnetic environment. A binary system, perhaps? A neutron star orbiting close to a massive companion star? Its signals distorted by plasma streaming off the companion? But here's where it gets strange. Another repeating source, FRB 20190520b, was found in 2022 to be varying its dispersion measure, the cumulative amount of plasma between us and the source, wildly and rapidly. This means the environment around the source was changing on timescales of days. Nothing in standard astrophysics changes that fast. The most remarkable discovery involves what researchers call sub-millisecond microstructure. Some bursts, when analyzed at the finest possible time resolution, contain internal structure, rapid subpulses firing in patterns within the burst itself at timescales of microseconds. These microstructures imply an emission region smaller than 300 kilometers across. That's smaller than the Earth. Think about that. An object smaller than Earth, 3 billion light-years away, producing a radio signal powerful enough to be detected across that distance with equipment we built a few decades ago. The evidence extends beyond magnetars into the realm of physics we don't yet possess. So what are we dealing with? Let's survey the theoretical landscape. The leading hypothesis remains magnetars, neutron stars with the universe's most extreme magnetic fields. Dr. Kiyoshi Masui at MIT and colleagues have developed models in which catastrophic reconfigurations of a magnetar's magnetic field create powerful shock waves that accelerate plasma to near-light speed, generating the radio burst. This explains the galactic magnetar event and, with some stretching, the extragalactic bursts. But the magnetar model struggles with repeaters. Stars don't typically survive this kind of violence repeatedly. Some researchers, including Dr. Ziggy Plunas at the University of Toronto, argue that different mechanisms may be responsible for one-off bursts versus repeaters. That fast radio burst may be an umbrella term covering multiple distinct phenomena, the way fever covers everything from a cold to malaria. Others, including theorists at the Canadian Institute for Theoretical Astrophysics, have proposed binary systems: a neutron star orbiting a black hole, or another neutron star, generating bursts through interactions with an accretion disk or magnetosphere. This would explain the complex, changing environment some sources appear to inhabit. Then there are the more exotic proposals. Lead author Professor Manasvi Lingam and Dr. Avi Loeb of Harvard has published work suggesting that some fast radio bursts might originate from cosmic strings, hypothetical one-dimensional defects in space-time left over from the Big Bang, vibrating and collapsing at near-light speed. This is speculative, but it is grounded in legitimate theoretical physics. And then there is the paper that electrified the internet in 2015, published by researchers at Harvard, proposing that repeating fast radio bursts could, in principle, be consistent with the emissions of a directed energy sail. Essentially, a beam used to accelerate a spacecraft, the radio waves leaking into space as a byproduct. The researchers were careful. They were not claiming aliens. They were saying the observed properties of FRBs were not inconsistent with an artificial origin. That is a very different statement, but it is one that serious scientists made in a peer-reviewed journal. This forces us to reconsider fundamental assumptions about what we accept as a natural phenomenon in a universe we've only been seriously studying for a century. The next decade will be transformative. The Square Kilometre Array, SKA, now under construction in South Africa and Australia, will be the most sensitive radio telescope in history when it comes online. It will detect fast radio bursts at a rate that makes CHIME look like a pair of cupped hands. More importantly, it will localize them precisely enough to identify host galaxies for nearly all detected bursts, allowing astronomers to map the structure of intergalactic plasma with unprecedented resolution. This matters beyond FRBs themselves. Recent breakthroughs suggest that fast radio bursts could become the universe's most powerful cosmological rulers, because their dispersion, the delay caused by plasma, is proportional to the amount of matter between us and the source, and because the universe's density of matter is related to its age and expansion, a well-calibrated catalog of FRBs could help resolve one of cosmology's deepest current crises, the Hubble tension, a persistent disagreement between different measurements of how fast the universe is expanding. In 2020, a team led by Jean-Pierre Macquart at Curtin University published a landmark paper using 5 localized FRBs to detect the missing baryons, ordinary matter predicted by cosmological models but never directly observed. The FRB's dispersion signatures revealed this matter hiding in the diffuse filaments between galaxies. They had used a cosmic mystery to solve another cosmic mystery. This is the magic of fast radio bursts. Even before we understand what they are already becoming one of our most powerful tools for understanding everything else. The most profound implications emerge when we consider what a complete theory of fast radio bursts would require. We would need to explain objects of extraordinary compactness, smaller than Earth, often, releasing energy at rates that challenge our models of stellar physics. We would need to explain environments that change on timescales of days at distances of billions of light years. We would need to explain microstructure at microsecond scales that demands emission regions measured in tens of kilometers. And we would need to explain a universe that is, by our best estimates, producing tens of thousands of these events every single day, across a volume of space we can barely conceptualize. Consider this. If even a small fraction of fast radio bursts originate from something other than magnetars, binary systems, cosmic strings, mechanisms we haven't conceived of, then our current taxonomy of cosmic objects is incomplete. There are things in this universe we have not yet named because we have not yet understood them well enough to name them. And if this is speculative, but scientifically grounded speculation, if the complexity of some burst environments, the precision of some repeating patterns, and the sheer information content of some signals contain structure beyond what natural processes are known to produce, then we face a question that every generation of astronomers has feared and hoped in equal measure. Are we alone in listening? The SETI Institute actively monitors known FRB positions. Breakthrough. Listen, the most comprehensive extraterrestrial intelligence search in history has pointed the Green Bank telescope at FRB 121102 for dozens of hours. They found nothing conclusive. The original 2017 observation found 15 to 21 in real time, a treasure trove of data still being analyzed. The answer is almost certainly natural. The history of science is littered with phenomena that seemed inexplicable until they weren't. Pulsars, quasars, gamma-ray bursts, all once mysterious, all eventually explained. But almost certainly natural is not the same as definitely natural. And that distinction is what keeps the radio telescopes pointed at the sky. We began with a signal, a millisecond of radio energy from across the observable universe, arriving at a telescope in the Australian outback and vanishing before anyone could properly react. 17 years later, we have hundreds of sources, we have repeaters, we have pinpointed host galaxies. We have used these bursts to weigh the matter between galaxies and probe the structure of space itself. We have built instruments specifically designed to find them, and those instruments have exceeded every expectation. And yet, we still do not know with certainty what makes them. We know they are real. We know they are immensely powerful. We know the universe produces them in staggering numbers. We know some of them repeat with almost mechanical regularity, and some fire once and are never seen again. We know their environments are complex, dynamic, and in some cases deeply strange. What we don't know is whether the catalog of known astrophysical objects is sufficient to explain them, or whether something entirely new awaits us in the data. That is the current scientific consensus. Magnetars are likely, but the story isn't over. And perhaps that is fitting. Fast radio bursts arrived in our awareness as a mystery. They have earned their mystery in a cosmos 13.8 billion years old, spanning 93 billion light years, populated by trillions of galaxies, each containing hundreds of billions of stars. The idea that we understand everything that can happen seems less like scientific confidence and more like hubris. The universe is vast. The signals keep coming. And somewhere in the endless dark, for reasons we may not yet be equipped to understand, something is shouting at the speed of light. We are listening? If you have enjoyed this video, please like and subscribe. Thank you for watching.